and welcome to my ACTL5111 Project brief presentation. The task I'm focusing on is the prediction of the market value of football players. So the main points covered by this presentation include an introduction to the problem, overview of the dataset, and I'll discuss three models, namely a baseline simple machine learning model and two neural network models, each with different architecture. Then I'll discuss how I can improve the performance of my models. Now let's proceed. The task of this project is to predict the current market value of football players based on some of the key player performance metrics. These metrics could be indicators such as number of goals scored, number of assists produced, and the number of yellow cards per game. And eventually, with a well-tuned model of this kind, we can gain more insights on how different aspects of a player's game affect his or her valuation. It could also potentially reveal some of the complex hidden relationships among these indicators. And most important of all, this model can provide a handy tool for player value estimation. So the dataset I use is obtained primarily from the public website of Transfer Market. This is a website specializing in footballing data. And this version of clean data I use is downloaded from Kaggle website, and two authors have contributed to the cleaning of the data as shown on the slides. The dataset contains 10,000 entries, each with 21 variables of player value indicators, such as age, height, goal scored in 90-minute scale, highest historical values, average clean sheets per game. And these are collected based on the 2021-22 season and 2022-23 seasons, consisting of players from major top-tier football leagues around Europe, America, Africa, and Asia. In order to prepare the data, I first removed all the unrealistic data entries. For example, all entries where players have zero highest historical values are removed. Moreover, for the models to be more meaningful, I created separated dataset for goalkeepers and the outfield players. The outfield players means the players who are not goalkeepers. And the reason I did this is because the feature selection will be different for these two groups of players in the modeling phase. Now, as you can see, when predicting the price of goalkeepers, we use the predictors including their height, age, appearance, number of yellow cards received per 90 minutes, number of goals conceded, number of clean sheets, minutes played, number of awards over their career, and their highest market value. While for the outfield players, we do not care about the number of clean sheets or the goals conceded, but we care more about their number of goals per 90 minutes and the number of assists per 90 minutes. Okay, so after knowing a bit about the dataset, I'll now start introducing some of the models I've built. First of all, a random forest model with 100 parameters are fitted as my baseline model, and it is fitted on the goalkeeper dataset and outfield player dataset respectively. I use the mean absolute error as my performance assessor to assess the regression performance. And as we can see on the goalkeeper dataset, the random forest model provides a validation MAE of 706,296 and a test MAE of 416,507. On the outfield player dataset, random forest gives a validation MAE of 1.08 million and the test MAE of 967,242. Now, for our first neural network model, I constructed a basic sequential feed-forward network. I conducted hyperparameter tuning with regard to the number of hidden layers of the model, number of neurons in each hidden layers, activation function for the input and hidden layers, the batch size, and the model's learning rate. The models displayed on the screen are the selected ones with the lowest mean absolute errors. As we can see for the goalkeeper dataset, our sequential model has a validation MAE of 840,550, while the test MAE of 813,764. For the outfield player model, we have a validation MAE of 1.88 million and the test MAE of 2.04 million. For our second neural network model, I apply the wide and deep structure on the outfield player's data. This means that the simple one-hot encoded variables goes through the wide path with only one hidden layer, while the more complex numerical and categorical features go through the deep path, which will be passed through two more hidden layers. This way, we can better characterize the both the linear and nonlinear relationships within these parameters. It turns out that the test MAE for the outfield player data for our wide and deep neural network is 1.78 million, which is a slight improvement over our basic sequential neural network. Based on the discussion, we can see that among the models I built so far, the random forest, which is our baseline model, performs the best in predicting players' current market values. To improve the performance of my neural network, I'll further tune the parameters, hyperparameters, and apply entity embedding while reducing overlapping dimensions to improve model efficiency. This is the end of my presentation. Thanks for listening.